Hi everyone, I am Dr.A.RAKINI, Assistant Professor of Chemistry, A.D.M. College for Women, Autonomous, Nagapattinam. Now I am going to present my topic on D block elements. This topic present in second BSc Chemistry. Okay, let us see the introduction. D block elements are present from 4th period onwards. There are mainly 3 series of the transition metals. Example, 3D series like scandium, titanium, vanadium, chromium, manganese, ferrous, cobalt, nickel, copper and zinc. And then 4D series like yttrium, zirconium, neodymium, molybdenum, tungstenium, ruthenium, rhodium and palladium, silver and cadmium. 5D series lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium, palladium, gold and mercury. Okay, D block elements are known as transition elements because their position in the periodic table is between S and D block elements. Electronic configuration. The electronic configuration of the D block elements is N-1, D 1-10, Ns 0 to 2, but copper plus zinc, cadmium and mercury etc. N-1, D10 are D block elements but not transition metals because they have completely filled d orbitals. The general properties of the transition elements. First one, atomic and ionic radii. In transition metals, left to right, net nuclear charge increases due to poor shielding effect. Due to this, the atomic and ionic radii for transition elements for a given series show the decreasing trends for first 5 elements and then because almost constant for next 5 elements of the series. The second one, enthalpies of atomization. The transition elements exhibit higher enthalpies of atomization because of larger number of unpaired electrons in their atoms. They have stronger interatomic interaction and hence stronger bond. Third one, ionization enthalpies. In a series from left to right, the ionization enthalpy increases in nuclear charge. The irregular trends in the first ionization enthalpies of the 3D metals prove of little chemical significance can be accounted for by considering that the removal of one electron alter the relatively energies of 4s and 3d orbitals. Fourth one, oxidation state. The transition metals shows variables oxidation state due to two incomplete outermost states. Only stable oxidation states of the first row transition metals are scandium with oxidation state of +3, the titanium oxidation state of +4, vanadium oxidation state of +5, chromium these have two oxidation states, first one +3 and then +6. Manganese it's also two oxidation state +2 and +7. Ferric and ferrous ions have also two oxidation states +2 and +3. Cobalt have two oxidation state +2 and +3. Nickel have one oxidation state, it is called +2, and the copper +2, zinc +2. The transition elements in the lower oxidation state +2 and +3 usually forms ionic compounds. In higher oxidation state, compounds are normally covalent. Only osmium and ruthenium shows +8 oxidation state in the compounds. Nickel and ferric ions is in the tetracarbonyl nickel NiCO4 and pentacarbonyl ion FeCO5 shows the 0 oxidation state. Fifth one, trends in the standard electrode potential and the transformation of the solid metals atom to M2 plus ions in solution under the standard electrode potential. If sum of the first and second ionization enthalpies is greater than the hydration enthalpy standard potential E0 2 plus will be positive and relatively will be a lower and vice versa. Sixth one title is here, trends in stability of higher oxidation state. The higher oxidation number are achieved in the titanium tetrahalide, vanadium pentafluoride and CrF6. The +7 state for manganese is not represented in the simple halides, but manganese trioxide fluoride is known, and the biode manganese no metal has a trihalide except iron +3 halides, and cobalt 3 fluorides, and increasing order of oxidation power in the series V oxidation and vanadium oxide plus is greater than the chromium oxides and greater than the manganese oxides. Next one, seventh one, the magnetic properties. When a magnetic field is applied to the substance, mainly two types of magnetic behavior are observed: diamagnetism and paramagnetism. Paramagnetism due to presence of unpaired electrons. Each electron having a magnetic moment associated with its spin angular momentum. The magnetic moment is determined by the number of unpaired electrons. The magnetic moment equal to root of n into n plus 2. This is a magnetic moment. And where n number of unpaired electrons. If all electrons are unpaired, the substance will be diamagnetic and the magnetic moment will be 0. Next one, 8th, formation of colored ions. The d orbitals are non-degenerate in presence of ligands. When an electron from a lower energy d orbital is excited to a higher energy d orbital, the energy of the required wavelength is absorbed, the rest light is transmitted out. Therefore, the color absorbed corresponds to the complementary color of the light absorbed. In vanadium pentoxide, vanadium is +5 oxidation state. It is colored to the epoxy crystal lattice. The next one, formation of complex compounds. The transition metals have small size, higher nuclear charge which facilitate the acceptance of lone pair of electrons from ligands. They have vacant d orbitals of appropriate the energies order to accommodate the lone pair of electrons. Next, 10th one, catalytics of the properties. The transition metals have two outermost cells, incomplete and the ability to adopt multiple oxidation states and to form complexes, therefore used as a catalyst. The transition metals also provide a large surface area of the reactant to be absorbed. Formation of industrial compounds. The small size of non-metals, hydrogen, carbon, nitrogen, fit into the whites of a crystalline solid of transition metals and form industrial compounds. The principle of physical and chemical characteristics of these compounds are as follows. First one, they have high melting point, higher than soft pure metals. Second one, they are very hard, some porous and the abrasive and the diameter is a hardness. And the third one, they retain metallic conductivity. And then fourth one, they are chemically inert. And then last one, alloy formation. The alloy is a homogeneous mixture of two or more metals. Transition metals have approximate some same size of their form. In the molten form, they can be bit to each other crystalline structure and form homogeneous mixture and form the alloys. Example, brass, it is a copper zinc, and bronze, it is a copper tin, etc. Next one, comparative study of zinc group elements. Zinc group elements, they are four chemical elements. The constitute group of 12P. It is of the periodic tables, namely zinc, cadmium, mercury, and copernicium. And they are properties in common, but they also differ in significant respects. Zinc, cadmium, and mercury are metals. with the silverly white appearance and relatively low melting points and boiling points. Mercury is the only common metal that is a liquid at a room temperature, and is a boiling point is lower than that of any other metals. Zinc, cadmium and mercury can loss of 2 electrons in the outermost shell to form 3 positive ions M2 plus, in which M is a represent a generalist metal elements, and they exposing the next innermost cell with a stable configuration each has of 18 electrons. These 3 elements tend to use the 2 outer electrons for the covalent bonding. Zinc exhibit the only 2 plus 2 oxidation state. It can give up 2 electrons to form an electrovalent compound, example zinc carbonate. It may be also share the electron is in the zinc chloride, a compound in which is the bonds are partially ionic and partially covalent. The cadmium compounds are mainly ionic, but cadmium also form complex ions with silicon. Atoms ions are molecules that detonate the electrons to a central metal ion. Its example, the complex ions are in the ammonia NH3 having the formula tetraammonium cadmium 2 ions, or the cyanide ion the formula of tetracyanide cadmium 2 ion. Mercury is a plus 2 and plus 1 oxidation state forms the ionic mercury the cation and the mercurous ions respectively. In the latter 2 electrons shared in the covalent bond between the 2 metal ions. The mercurous ion shows the little tendency to form complexes versus the mercury cation form them. In the contrast to compounds of mercury in the plus 2 state, which are usually covalent, all the common salt of mercury in the plus 1 state are ionic. And the soluble compounds, example mercurous nitrate. So normal properties of ionic compounds such as is of the dissociation or breakup into the separate ions in solutions. Mercury is a exceptional that unlike zinc or cadmium, it does not react easily with oxygen on heating, and mercurous oxide does not show the acid property of forming salt mercurites versus zinc oxides that is here readily. Next one, extraction of molybdenum. And the molybdenum can be found in a number of minerals, but only molybdenate is suitable for the industrial production of marketable molybdenum products. The molybdenate can occur as the salt mineralizations in the ore body, but is usually associated with the sulfate minerals of other metals. Mainly copper molybdenum mines are classified into 3 groups according to the minerals contained in the ore body and their quality. In the primary mines and where the extraction of molybdenate is the sole aims. Byproducts mines also there is a extraction of copper bearing force in the primary aim, and the molybdenate extraction provides additional economical value. The co-products mines where both molybdenate and copper bearing minerals are extracted. And the roughly 40% of molybdenum comes from primary mines, and then which is the other 6% byproduct of copper are in the some cases tungsten. In the ore lies close to the surface, open pit technology will be used, and if the ore lies deep underground method will be used. And the extraction of next one is the extraction of platinum. This is only most important title, the extraction of platinum. The platinum is a very less reactive with the elements, so it is considered a noble metal along with the other 5 elements in the platinum group. And they resist and chemical attack even at a high temperature. So platinum is used as a catalyst in mainly chemical reactions. Platinum group of elements. There are 6 platinum group of elements in the periodic table. There are platinum, palladium, rhodium, ruthenium, iridium, and osmium. So platinum belongs to the platinum group. It belongs to the 10th group and 6th period. Occurrence of platinum. Platinum is one of the rarest elements available in the earth crust. The availability of platinum may be around 5 kg. It is 0.005 ppm. This ppm means parts per million. South Africa is the biggest producer and supplier of platinum in the world. About 8% of platinum demand is met by the South Africa only. And the second largest deposit of platinum are found in the Ural Mountains in Russia. In India, abundant platinum deposits are found in Tamil Nadu. Platinum deposits are more on the moon and Mars. Physical properties of platinum. Platinum is a dense, malleable, flexible, ductile, and silverous white metals. It is more ductile than the other precious metals like gold, silver, copper, but is less malleable and cold. It will be malleable when combined with gold. It is the one of the tensest metal with the density of 21.45 grams per cubic centimeter. Chemical properties of platinum. Chemically, it is highly unreactive. That is why it is categorized as the precious metals. The platinum is highly resistant to corrosion. It is not then the tarnished in the air. That is why it does not form oxides, hydroxide, and carbonates and sulfides when exposed to the atmosphere. It gets oxidized at 500 degrees Celsius. It is reactive with halogens like fluorine, chlorine, bromine, and iodine at very high temperatures. It is soluble in hydrochloric acids and nitric acid. It absorbs the abundant hydrogen gas at high temperature, just like sponge soaked water, which is an unusual property of platinum. Platinum shows a strong tendency to form complex ions. The most common one is a platinum. These complex ions show a planar structure. This is a diamagnetic. The temporary and weak magnetic pole formation. Next stages of extraction of platinum. Platinum is extracted very deep in the soil first. It is extracted by the froth flotation process. The ore is heated up to 1500 degrees Celsius in the electrical furnace. Platinum is extracted from the mineral concentrate by the using aqua regia, HCl plus HNO3. Ammonium chloride is used to convert chloroplatinum acids to ammonium hexachloroplatinate. The resultant substance is bound to get the pure platinum metals. The next one, platinum uses. Platinum is used in different applications like jewelry, vehicles, and emission control devices, petroleum refining, and electrical appellants, and glass magnetic equipment, electrodes, oxygen sensors, spark plugs, and their turbine energies, the medicines, anti-cancer drugs, etc. The most common use of platinum is on the catalyst of many chemical reactions. It is used as a catalyst during the preparation of nitric acid, benzene, and silicones. It is also used as the catalyst converter in vehicles. The international standards measures like a meter, kilometer, and thermometer are made of the platinum. Platinum is used as a precious metal in jewelry making. The platinum jewelries, it can be used as a future investment. Platinum stones next to a diamond and above fold is the title of the awards. The platinum colors is a symbol of stands of deposit and credit cards also. Debit card and credit cards also. The platinum is used in laser applications. It is used in the photographical industry. It is used as laser coatings. And then strong magnets are made with platinum and cobalt alloys. Platinum is used in the fabrication of a breast implant and prosthetics. Like next one is alloy of copper. Alloys of copper is a very important topic. It is 10 mark or 5 mark questions also with the alloys of copper. For many applications, the properties of copper can be readily customized. This is achieved by the alloying and the making a new metals of two or more different metals. The most well-known copper alloy familiar or bronze. It is a copper zinc and the bronze. It is a copper tin and copper nickel. These actually represent familiars of alloys, all made by the varying the amount of specific alloying elements. Alloys can be made to the achieve certain colors, improve strength or corrosion resistance, improving the forming of joining and the properties or achieve under any number of specific demands that the individual elements cannot achieve on other own. By the combinations copper with other metals and adjusting the percentage. Alloys are most to fit almost any applications. The higher purity of copper is soft, malleable and ductile metals with a very high thermal and electrical conductivity. The freshly exposed surface of pure copper has a reddish orange color. Copper is used as the conductor of heat and electricity as a building materials and as the constant of various metal alloys such as steel, silver used in jewelry, copper nickels and used to make the marine hardware and coins and constant as used in strings, carats and the thermal cables for the temperature measurement. The copper alloys are alloys based on the copper. It is the main alloying elements of zinc, tin, silver, aluminium, nickel. Copper-based alloys constitute mostly substitution solid solutions. For which years and the solid of impurity atom replace sovereign substrates for the cost atoms. Several features of the solute and solvent atom determine the degree of which the form and the dissolved in the latter. Thus, is all expressed as a Kim-Rotary rules. And there are mainly 400 different copper and copper alloys compositions loosely grouped into the categories. Copper highly alloys process bronzes and the copper nickels, copper nickel zincs and leaded copper and special alloys in the addition here. Limited and the number of copper alloys can be strengthened by the heat treatment. Consequently, the cold working and are the solid solutions alloying mostly be used to improve these mechanical properties. Thank you so much.